So good morning, everybody. Thank you for coming over here so quickly over the keynotes. I actually cut out before it ended. So I wanted to welcome you to my talk called Machines Can Do the Work, Automation in the Kubernetes Contributor Experience. Now, when I practiced this talk, the first time I practiced it, I ran 75 minutes. Second time I ran 45 minutes, so if I move quickly, I apologize. I'll definitely try and leave time for questions at the end. But also because I know I may not make it to the end, I wanted to take some time up front. And even though I'm the one up here giving this talk, my name is Crickenberger, by the way. I co-founded SIG Testing. I participated in a number of Kubernetes releases. I'm a member of the Kubernetes Steering Committee, and I'm an active participant in the contributor experience. But all these people up here are responsible for contributing to or writing a lot of the infrastructure and tooling that I'm going to talk about today. And if you don't recognize their GitHub avatars off the top of your head, here are the usernames for you to go stalk them later. I don't have these slides posted online right now because, of course, I wanted to keep you all in suspense, but I promise I will upload this as soon as I'm done with this talk so you can keep this cheat sheet with you at all times to go thank these people for all of their hard work. So I wanted to tell you the story of Kubernetes as a project and how sort of early on, we decided that if this was going to be a successful project, we needed to go to where the developers are, which is GitHub. And so we figured that if we did things the GitHub way, we would succeed beyond our wildest dreams. And unfortunately, this came true. But we found that over time, we've come to adapt to, this is Fine Dog is basically our spirit animal in the testing world for Kubernetes. There's a lot of stuff that goes on in the project, but things are actually okay if we can figure out the right problems to solve and deal with it. Figure out ways to get automation to help us do the boring work, and we can get to do the interesting work. And the reason that things are fine today is because we live in this nice tropical abyss of using a thing called Prow. This is a diagram put together by Ben the Elder. He posted it on his blog back in December. And I'm just showing it up here real quickly, not to walk you through it, but to show you that this diagram exists. If you would like somebody to walk you through it, I encourage you to check out SIG Testing. But basically, this is a bunch of little microservices that help us sort of do testing in a more Kubernetes native way. So here's the logo for Prow. Prow was initially started by members of SIG Testing and the engineering productivity team on the Kubernetes side of Google. But today it's actively used and contributed to by members of Istio, JetStack, and OpenShift. And the project has become significantly better for it. Prow is made up basically of a bunch of different plugins that allow it to accomplish certain things in response to GitHub events. If this looks a lot like Probot to some of you who might be familiar with that, it's because it started before Probot. It's sort of considered to be prior art. The main way of interacting with Prow as an end user is via these slash commands, and we have most of them are updated on the fly in Prow's UI. So you get to see which command corresponds to which plugin, what it allows you to do, and who gets to use it. And if you want to find out more about exactly what Prow is made of and how it works, I encourage you to come to the SIG Testing Deep Dive Friday at 2 o'clock. So when I talk about machines doing the work, what do I mean by the work? If you break it down into 4 categories, it's basically, implementing your typical PR workflow of testing pull requests, making sure they look good, and then merging them. It's helping out with issue triaging and pull request triaging, make sure that they, they're categorized appropriately and they get to the right people. It's about making sure that we can create and configure and manage hundreds of jobs. And it's about taking all of this data that we produce and using it to gain insight into the health of the project. So I wanted to walk you through our pull request workflow sort of as the lens for the bulk of the automation. And this looks relatively non-controversial, I think. As with any large open source project, people need to sign a CLA to make sure that their code gets contributed. The pull request needs to pass all of the tests. It's got to be approved by human beings. It's got to be mergeable. There can't be any merge conflicts. And we've got to make sure that it passes tests right before we push the merge commit. So when it comes to signing the CLA, there's really not much for me to say here other than the Linux Foundation provides an awesome CLA bot, and all we do is talk to it as like a webhook. So as long as we see a check mark come back from that, we're satisfied that every author of every commit in a given pull request has signed the CLA, and we can move on from that step. So when it comes to running tests, it sure looks like there are a lot of tests here. Now, when we started this project off, we knew it was a distributed system, and so it was going to involve a lot of moving parts. You just saw Dan's keynote where he talked about continuous integration is really super fundamentally important to the cloud native way of doing things. So, we definitely wanted to test all of the things. And so we got super enthusiastic about making sure that we're not just testing individual components of Kubernetes in isolation. We're not just writing unit tests. We're not just writing integration tests. We're writing end-to-end tests because this is a distributed system. So we're going to stand up entire clusters. We're going to exercise everything. We're going to not actually trust that anything works until we've tested the whole thing end-to-end all the way through. The problem is pretty much everybody felt like they couldn't confirm that their code was feature complete or that it logically worked until they did end-to-end tests. And the problem with end-to-end tests is, at least back in the bad old days, there's just thousands and thousands of lines of bash everywhere. There was bash used to stand up a cluster. There was like a 1,000-line bash file to define how to actually run a test job. And worst of all of this stuff was configured with environment variables. And so you could be something like 6 layers deep of inclusion in bash scripts, and you wouldn't know where a given environment variable came from. You wouldn't know what an environment variable here did over there. And because it's bash, you can write unit tests for bash, but it's by no means type safe. It's by no means refactor friendly. And so it was kind of really painful to manage this stuff. Further, much like anybody else, the knowing laughs indicate you too have lived through Jenkins. I don't have hard numbers for you, but I can tell you that early on, we had somewhere between 100 to 150 Jenkins nodes just for running builds. And we were talking directly to Jenkins. And Jenkins doesn't take kindly to being talked to about hundreds of pull requests a day or thousands of tests a day. Jenkins job configuration is really atrocious to manage. We went through a period of time with Jenkins Job Builder where we defined jobs as YAML files that then got rendered to XML, that we then used bash to diff to see if the XML actually looked sane, because of course we didn't have a linter for valid XML configurations until we loaded it into Jenkins and it blew up. And yeah. So the other thing I wanted to hit home though was that this Jenkins instance that was responsible for driving most of the testing for the project was visible primarily to people inside the walls of Google. So if you were a contributor to the project who worked anywhere else, you would hear people talk about the blocking jobs or the build blocking jobs, or people who could click through and see historical artifacts and results. And a large community of people couldn't see this. So over time, we kind of got to, do we really need to test all the things? Isn't there some way we can spend less energy running tests? And so I wanted to take you briefly back to around September of 2016, when instead of that pull request shot I showed you earlier, we were only running like 6 to 7 tests for every pull request. And they were still, does it run end-to-end on Google? Does the node look good end-to-end? We're doing smoke testing, like Dan said. We're doing unit and integration testing. That's great. The problem was your code wasn't allowed to merge until all of these other tests were passing on what were called periodic or continuous or post-submit blocking jobs. These were sets of jobs or tests that would run every hour, every 15 minutes, as often as possible on the latest and greatest commit. And if any of these were failing, your code wouldn't be allowed to merge. And it got into this unfortunate situation where you can see here, like, all these tests are passing, but these tests are failing. Well, that's just the build cop's problem. That's not my problem as the pull request author. It's somebody else's job to go chase down why those, 20, 25 other jobs are failing, and then to figure out who to chase down to ask them very kindly to revert their code or troubleshoot why the test wasn't working. And it ultimately ended up in this really frustrating situation where I could check code in that would break the build, and I would have no idea that I had done it, and nobody would really notice until the build cop got paged and came looking for you. So fast forward today where we're using Prow. And Prow's kind of helped us get out of this situation, if for nothing else than the fact that it's significantly better at running tests concurrently, and it's much easier to manage than Jenkins. So we really are testing all the things. So we're making sure, first and foremost, that your code, passes our coding conventions. Are you following the right API conventions? Is it formatted cleanly? Things like that. We're also making sure that it builds. And we're doing a quick type check to make sure that it kind of pseudo compiles across all different architectures that we support. So most of our testing is done for the Linux AMD 64 architecture. We also release artifacts for things like ARM, and we want to make sure we're not breaking those builds unbeknownst to us. Then, you've got your pretty standard, we want to make sure it passes unit and integration tests. We want to make sure that it passes end-to-end tests on 2 different cloud platforms. So if it doesn't work in either Google or AWS, we want to prevent this code from merging. We want to make sure that we can sort of do specific end-to-end tests just on the node level. Because a cluster is a distributed system and it could fail for a variety of reasons, we really want to look at specific things like, does the container runtime interface work well for this engine versus this other engine? And then, of course, we also want to make sure that we can do we can stick within the realm of our performance boundaries by using simulated performance test called kubemark, which stands up like a real Kubernetes cluster, but with fake nodes, so we can pretend like we're scheduling to a 100 node or 500 node cluster without expending all of those resources. And then finally, we also allow the ability to run optional tests for every pull request, but these don't necessarily prevent it from merging. Usually these are tests that get skipped because they don't have to run on every pull request. They'll only run if certain lines of code or certain files have changed, or it could be because we're trying them out as non-blocking builds right now to maybe collect data to promote them to a blocking build down the line. So this is roughly 2 years worth of data. It starts when, instead of using Jenkins as an authoritative source for artifacts, we started pushing all of our data to publicly accessible Google Cloud Storage buckets. And from there, could scrape to, from there, we could scrape the data into BigQuery tables where I could start to put together graphs like this for you. So around October of 2016, we started using Prow as the primary front to kick off jobs. We initially had Prow then talking to Jenkins, but because Prow was the thing receiving these hundreds and thousands of requests, we could throttle and not kill our Jenkins so often. Soon we started migrating from running jobs on Jenkins to running jobs directly on Kubernetes clusters as pods. And eventually we got so confident in the sheer number of pull request jobs that we were capable of running that we disabled the whole concept of blocking jobs on head. So if your pull request passed its pull request tests, that's the only thing it needed to do to merge. And then 6 months after that, we retired the build cop role because it was just punishment and pain on whoever was unfortunate enough to come up in the rotation for that. And people have been a lot happier for it. So when I say Prow has made things a lot better for us, what do I mean by that? Fast forward to today, and over the past year, from March 2017 to March 2018, we ran 4.3 million jobs using Prow. And these are jobs running entirely on a Kubernetes cluster now. There's no Jenkins involved. This graph here shows you that about 600,000 of those jobs were for pull requests. The blue line is for Kubernetes-related jobs, and the green line is for any other project that could be in the Kubernetes or incubator or Kubernetes SIGs orgs or other projects such as Kubeflow. You can see that the other 3.7 million jobs were some of those continuously running after the fact jobs. These are the sorts of long-running performance tests or off-the-beaten-path feature tests that we want to make sure we can use to verify a release of Kubernetes before it goes out the door. Because you can see that over time, we found that it's kind of less useful from a signal perspective because more people are paying attention to their pull requests than are paying attention to these continuously running jobs. You can also see just by the number of unique jobs, not necessarily the number of runs that have happened, that many more projects beyond Kubernetes have started to use our infrastructure. It's gotten to the point where our infrastructure is friendly enough and reusable enough that it works for projects beyond just Kubernetes. So I know, COPS and Kubeflow and the community repo all use this stuff today. And you can see that's not really the case for jobs that run after pull requests have been submitted. Because again, we find that while this is a pattern that's useful for a project as large as Kubernetes, it's maybe not necessary for your project today. So that's a little bit about testing. Next, let's talk about our code review workflow. So, what is code review? You want to make sure that you find somebody to review your PR. You got to make sure that you find the right person to review your PR. But how do you know who that right person is? And then how do you notify them that they should take a look at your PR? And then how do you know that all of the right necessary people have taken a look at your PR? And so things that we've tried in the past is, well, why don't you just open your PR and wait and see if somebody comes and reviews it? That doesn't work on a project at the size of Kubernetes. There are just too many people and the code base is too large. Let's try using GitHub notifications. You've figured out the person who's most responsible for this area of code. Why don't you at them? That doesn't work because GitHub notifications tend to just go into the void. My notification inbox collects about 100 to 300 notifications on a daily basis. It's as good as useless for me. We could assign PRs to people to ask them to review it. That way they could use a GitHub issue query to figure out, all the things that are assigned to me. But how do you know who to assign? Well, maybe you could use GitHub's feature of like the recommended who's committed to this recently. You could stalk them through commit logs or something. Or maybe you could try using GitHub's code owners feature where you can specify through regular expressions, like which files to use. Unfortunately, GitHub's code owners thing, if you lay out say there's 10 possible people who could be knowledgeable about code in the kubelet subdirectory, if you assign a review if you change a file in there and use GitHub's code owners feature, it will assign to all 10 of those people at once. It doesn't just randomly choose a subset. Further, if you were to assign to GitHub teams instead of individual people, that's great if you're a member of the org and know who is on that team so you know who to go bug. But if you're a new contributor, you don't get any visibility into who's on a given team. So you have no idea who to ask or talk to next if you need some follow-up. Finally, what if we just use the fact that somebody has write access to the repo to say that this is a person that you should pay attention to. Do they have the commit bit flipped? Can they manually set labels? We found that none of these really helped us scale as effectively as using owners files. So here's an example of an owners file at the very top of this directory for the contributors guide in the community repo. Let's say I wanted to add something to any of these documents. I would open up a pull request, and our automation would look at the owners file closest to the code that I am changing. So in this case, the owners file specifies two groups of reviewers. There are reviewers and approvers, and then there are labels down here for triage. So reviewers are people who are looking at your code qualitatively. Is it written well? Is it checking for nil? Does it catch all the corner cases? I should know enough about Golang, but I don't necessarily have to know about every single internal of all parts of Kubernetes to review an arbitrary pull request. On the other hand, if I'm an approver, I should know exactly how this area of code relates to the rest of the project. Is it doing the right thing? Is it maintaining backwards compatibility? Is it forward-looking enough? That sort of thing. And then finally, we can use these labels for triage. Like I said, you could use issue queries to look for PRs assigned to you. We could also have issue queries for PRs that are assigned to a specific SIG or a specific area. And so, much like code owners files by GitHub, we can also do this by regular expression, not just by hierarchy. We can have people signify whether or not they're good with the code by using some of those slash commands that Prow implements. So /lgtm is what a reviewer would do, and we allow anybody who is a member of the Kubernetes organization to /lgtm. So while we request review from the most knowledgeable people as spelled out in the owners files, we want to grow our reviewer pool. So anybody who is knowledgeable enough about Go could theoretically review any pull request. However, when it comes to somebody who wants to holistically look at whether or not the PR is doing the right thing, we want to make sure we get buy-in from all the right approvers. So approvers who are recommended have to say whether or not it's good or not. You can find out more at that link there. So I talked about applying labels to pull requests. Here's one of my favorite pull requests. I managed to find this set of labels on it. And I had no idea what these labels meant for the longest time. So I finally put together some documentation here. But honestly, my perspective on the label set like this is that you really should, you only need the labels that you absolutely need to survive. And I've come to realize on the Kubernetes project that these are my industrial strength GitHub labels, and the project can't live without them, right? If you break it down, here's the description of the labels that sort of shows, what are they, what do they do, what's the Prow plugin that handles them, and who can apply or use these labels. So all the green labels are the labels that need to show up on your pull request in order for it to be mergeable. Have the reviewers looked at it, there's your LGTM label. Have the approvers looked at it, there's your approved label. Did you sign the CLA? Great. All of these labels are things that are applied for a triage purpose. Is it a bug? What kind of priority is this issue or pull request? What area does it apply to? This helps the right people find issues that they care about or are interested in more easily. And further, while these are labels that you normally have to be, you have to have write access to a repo to apply labels, through Prow, we've allowed anybody, you don't even have to be a member of the organization, to help sort of triage these things more appropriately. So anybody can apply a priority, anybody can apply an area or a SIG to help us more effectively find things. And further, we can have automation help us out. So Prow automatically labels pull requests by the number of lines of code that they change into t-shirt sizing, so that at a glimpse as a reviewer, you can get a feel for how difficult this pull request is going to be to review if you happen to have some spare time. There's not much to say about these labels other than to say that they sort of help the Kubernetes release team herd the cats that are the organized chaos of open source into something resembling a top-down hierarchy and a consistent release process. Because these labels are so important for us, we want to make sure that the same labels are present in every single repo in the Kubernetes project. So that's all 60 repos in the Kubernetes org, all 20 repos in the Kubernetes incubator org, and the number of repos that are showing up in the Kubernetes SIGs org, which is something like 8 today. So we use a syncing tool that allows us to specify, new labels and what they should be, to migrate old labels or rename old labels to new labels, and to also deprecate labels and delete them after some amount of time. This is what's allowed us to migrate the Kubernetes repo from 220 odd labels down to about 170 labels today. Labels are also great because they empower the community to write some of their own triage tools. So here's an example of an issue query that a community member, DIMS, often uses to find first-time contributors who might want to be shepherded through pull requests. If you're not a member of the project, we want to make sure that your pull request isn't turning Kubernetes into a Bitcoin miner. So we need a human to just take a brief look at your pull request and apply a /OK to test command to it to remove that needs OK to test label. So Dims mentioned he'd been using that query just on kind of a daily basis when he had time. We wanted more people in the community to use it. So Jace Dumars bought a domain that just redirects to that query, and now anybody who wants to help out or identify first-time contributors to help shepherd through the project can click through that. Finally, let's talk about the fact that we need to test your code before we merge it. In the game of CI/CD, you have to always be merging, right? Code is for closers. So I mentioned that everybody wants to test all the things in fully end-to-end distributed tests. And over time, you can see that the longest test that any given pull request has takes anywhere from 40 to 50 minutes, but it's kind of trending up towards an hour. And so if you assume that, plus the fact that because we have end-to-end tests that are flaky and kind of depend upon the nature of distributed systems where nothing ever works 100% of the time, and some things can be susceptible to environmental conditions like the relative humidity and the alignment of the stars, if your code is supposed to pass, there's a 75% chance that it actually will pass when we are having our worst times. What that roughly means is if I must serially pass a pull request, each and every pull request before I merge it, that our ideal merge velocity is somewhere around 20 to 40 pull requests a day. So how are we actually doing compared to that theoretical ideal? Well, if I go over to DevStats and take a look at the 7-day moving average of our pull requests merged, we're actually beating the ideal. And if I get rid of the 7-day moving average and look at what we're actually doing on a day-to-day basis, we're beating that ideal by a lot. And the way we're beating that ideal is we don't actually test a single pull request before merge. When we're right at the moment of merge, when we're just sanity checking that even though the code has moved on since the pull request was initially tested, we take up to 5 pull requests at once, merge them all together, and test them as a batch. This way, if it passes, great, we can merge all 5 of them at once. If it fails, we're not going to know for sure which one of the 5 failed the test. So unfortunately, we're going to have to take a loss on that. But by and large, you can see that most of our pull requests are now tested in batches. In fact, by relative amounts, over 50% of our pull requests are tested in batch. There's literally no way our project could maintain the velocity it does if we didn't implement batch testing, which we did around November of 2017, as I recall. Just as a sanity check, is our infrastructure doing well? This is mostly a Monday to Friday project. Not too many people are contributing large amounts of code on the weekend. So I would expect the majority of our merges to be happening Monday to Friday, assuming everything is going well with our merge infrastructure. And for the most part, we are merging less and less over the weekend. Those red spikes there, one of those is the KubeCon dip, and one of those was after a code thaw, where we just opened up the submit queue right before the weekend to let it drain over the weekend. So the other part of the work, issue triage. Some of you who've worked on the project may be familiar with FetaBot. FetaBot's actually doing stuff that humans could 100% do on their own. FetaBot's issuing comments. That's all he's doing. He's issuing a comment on issues or pull requests that haven't had any activity by a human in 90 days. And then if nobody does anything for another 30 days, he applies another label. And then if nobody does anything after another 30 days, he closes the issue. These are all things that, so the lifecycle things anybody can do. Closing the issue, any member of the Kubernetes org can do. You can also, as a human, respond and say, no, wait, I actually think this is a really important issue and should be considered for more than 120 days without any comment. So I can apply the frozen lifecycle label to it, say, the lifecycle of this issue should be frozen until the heat death of the universe because I know it's important enough for somebody to come take a look at it. As a result, the number of open issues on the Kubernetes project, at least in the Kubernetes repo, has gone from about 4,500 down to 2,500. And interestingly, over the past couple of weeks, it's kind of hit this nice steady state where issues are getting open, but nobody's really paying attention to them, so they end up aging out. Now, I recognize this isn't ideal. In an ideal world, people would come and take the most important issues and be working on them. So this is kind of a problem of capacity, and one where we'd like to make the project easier to contribute to so that people are working on the most important issues that we can work on right now. This is another graph from DevStats that shows the number of times that people issued the /lifecycle command, probably to freeze an issue. And so this probably tells you when we turned on FetaBot and asked him to start commenting on issues that hadn't had any activity. It forced people to start doing planning down the line that they hadn't done up front. This is the Prow job that does it, and I'm only pointing this out just to show that it's just a simple label query. It's something you could do by hand, but we have a bot to do this for us. Similarly, we also offer the ability for somebody to issue a /retest command, and any test that failed will automatically be re-triggered and rerun. This was one of the most useful commands. This was one of the most useful commands on the project. You can see its usage spiked hugely once we introduced it. But the reason it's gone down since then is because we have FetaBot automatically issue this command to any pull request that's had an LGTM applied and it's approved, so it's good to go. The tests are flaking for whatever reason. And so it'll come through and automatically just apply the retest command until things actually work and it gets pushed through. Again, it's just YAML. So as far as the rest of the work that I laid out, I don't think I have any time to get to that. That's okay, this is fine, because if you go to the SIG testing deep dive on Friday at 2 o'clock, you'll get to hear a lot more about how we actually configure, manage, and run our jobs, and how you can use this on your project. So thank you very much.